Today, we are going to talk about some cool stuff. Logic, eventually inside of a computer, in the form of circuits. And then I'll start talking a little bit about binary. If you've never heard of that, it's just a number system. We will learn it. It's going to be great. All right, so let's get started. And so the first thing I want to talk about is this topic called logic. We've heard this word in English, right, before. It's just means, are you thinking clearly? But in computer science, it has a special meaning. So we want to learn to think logically in general. And then there's a branch of mathematics called logic. Right? So there's something to study here. And in logic, everything is either true or false. You're going to hear those words forever now. All right? True and false. Those are the only two things you can have in your logical statements. All right? But first, you may be wondering, like, okay, if everything in logic is either true or false, all these things I'm about to teach you, what does it mean for something to be true? Because we've been challenging everybody's beliefs, haven't we? So, like, what does it mean for something to be true? Let's figure that out. Like, what is truth? To get there, let's talk about some terms. All right, so here are some terms in the field of logic. The first one is called statement. Right, and so whenever I say the word statement, I mean a logical statement. It's one in this branch of math. Logical statement. It means something more than just a sentence, all right? Not the normal English definition. And so a statement, otherwise called proposition, those are synonyms. A statement or a proposition is just a sentence, kind of in English, that can either be true or false. All right? That's all I'm saying. So a statement is just something you can say that's either true or false. The answer is either yes or no, all right? Same with a proposition, same word. A statement cannot be both true and false, though. That means it's not really a statement. It's not really a proposition. So let me give you some examples of statements, just like my computer is black, my water bottle is purple. Those are statements, right? Those are true statements, too. This monitor is green is a false statement. Yeah, it's like I'm lying to you. So that kind of makes sense. Those are statements. Those are propositions. And a good example of a sentence that isn't a statement, that isn't a proposition, is this one right here. This sentence is false. This cannot be a proposition, and I'll tell you why. Well, if it was a proposition, it would either be true or false, but let me show you that it can't be either. If that sentence were true, what does it mean, right? So if this sentence is false, is a true sentence, a true statement, then it means it was really false. Does that make sense? So that didn't work out. We assumed it was true, it really was false. Does that make sense? Didn't work. It wouldn't work that way. Okay, maybe it works if we assume that it's false. Maybe it was really false. What does it mean to say this sentence is false, is a lie? Well, that means it was telling the truth after all. Do you see that? So, in either case, if it was false, it must have been really true instead. And so there's a contradiction in both ways that we could have it. Do you see that? So both of those lead to a contradiction, which has its own meaning in logic again. So it makes somewhat of the same amount of sense in English, though. So a contradiction just means like the universe falls apart, nothing makes sense. All right, so that's a sentence that isn't a statement, that isn't a proposition. But plenty of other things are propositions, like the chair is green, true proposition. Okay, stuff like that. Questions? These are just new terms. I'm gonna keep saying them. So yeah, we would like in a utopia, we would like to be able to like write down sentences and be able to mathematically somehow prove every sentence, either true or false, if it was really a proposition. It would be really nice if we could do that, and then just like prove to be false, all the things that are lies, all the things that aren't true. That would be great. If we could write down a sentence, and if it were a statement, we'd know, we'd have a way to say if it were true or false. That sadly is impossible. You'll have to wait till a very advanced math class to fully understand, but seems nice though. So does that mean that things that are true should be things that are provable? Is that we can like use math to show is true, or just use our eyes to show is true? Maybe. There's a bunch of different ways that people answer that question. There's a bunch of different definitions of the word true. It's disgusting. Philosophy majors love this. So I would like to teach you a few different theories of truth, and they're all competing with each other. They're all trying to define what truth means, what it means for something to be true, which we thought we knew by now, right? It's insane. So yeah, I've got a few. I do not claim to be a philosopher. I'm just a computer scientist, and so I'm going to give you my take on these, but it's weird just to think about people disagreeing over what true means, isn't it? Very philosophical today. So the first theory of truth that I want to talk about is called correspondence theory, and this one kind of makes sense. Maybe this is the theory of truth that you use in your mind when you're thinking about things. All right, maybe this is your definition of truth. So to the correspondence theorists, the people who like this theory, they consider every statement to be true. Call it S. The statement S is true if and only if. That's another loaded logical phrase. We'll get there. It's true if and only if S corresponds to a fact. All right, so that's what the correspondence theorists think, and they think that, all right, everything is true, that's a fact. But then you might ask the question, like, what's a fact? You can go down the definition rabbit hole, and I do not want to go down it. But to them, just like everything that's true corresponds with the stuff that they can see. All right, so Sherlock Holmes, for example, would be a correspondence theorist because he could go take his little magnifying glass, look at the crime scene, and be like, all right, here are the facts. I understand. I check. Like, it's true. I can see it. Something like that. All right. So, like, snow is white is usually true, right? Because, like, you can go drive up to Shaver or whatever and look at it and see that it is white. Okay. So that's what it means in correspondence theory for things to be true. Right? True things correspond with reality, things that I can check myself. All right. Does that make sense? Just somebody's definition of true. Maybe that's your definition of true. Only the things that are true are the things that I can see and understand. All right? That breaks down with things like religion, for example. But that's one theory of truth. And here is a silly meme that has to do with correspondence theory. All right, so read that while I prepare for the next slide, because there's more. There's plenty more where that came from. Right? There's different theories of truth that people believe. This is here's another. It's called coherence theory. There's a few kinds of coherence theory, but I'm going to show you one. To the coherence theorists, something is true, a statement is true, because it matches other true things. Okay? Because it matches other true things. And so here's an example of somebody using coherence theory to understand that something is true. All right? So for example, this statement, this proposition, 2 plus 2 equals 4, that's a true statement. It's a true proposition, right? But then why? To the coherence theorists, this is true because, like, they know, I know what 2 is, I know what 4 is, I know what the plus symbol means, I know what the equal symbol means, and just, like, following from those pieces, they're all jumbled together, I can make that statement and understand that it's true. Okay? So that's what the coherence theorists believe is the definition of truth, and it's kind of in contrast to the other one, because, like, can you see 2? Not really, right? So correspondence theory kind of breaks down a little bit, but it's just a way of thinking about things. So here, there's other kinds of coherence theories, other kinds of coherence theories. To a different kind, some people believe that a statement is true because it matches the beliefs of a majority of people in my society, and that's like inconvenient, right? For certain situations. So that's one more theory of truth. And there's plenty more where that came from. This one is the weirdest one to me. I don't fully understand it. I majored in computer science, not philosophy. But to the deflationary theorists or the redundancy theorists, their definition of truth is like no. Their answer is no. They don't even try. They say that no, you shouldn't even try to be defining truth. They're just trying to like turn the problem on its head. It's weird. So they're saying something like, well, if you were to tell me that 2 plus 2 equals 4 is true, that's just redundant. That makes no sense at all. Just why don't you just say 2 plus 2 equals 4? Use the verb to be. You don't have to use the word truth. There's no need to define it, which is interesting. They try to sidestep the problem, I guess. So to them, it doesn't even make sense to ask the question, what is truth? They don't care. Truth doesn't really matter. It's not even a thing. It's not real. There is no truth. So, yeah, I don't fully understand it, but that is what I learned from the internet, at least. And so, yeah, again, these are all competing with each other, all these different theories of what it means to be true, and maybe certain theories you use already. Then they apply to certain situations, but not others. Maybe you use a bunch of different kinds. Right? The last one that I want to talk about is called pragmatic theory. I think the utilitarians would enjoy this one. They believe that propositions are true if they are useful to believe. All right. So even if you're lying to yourself, to the pragmatic theorist, they're like, it's all about the utility. If it is useful for me to think this is true, then I'm going to think that it's true. Interesting. And so, yeah, it's very utilitarian. And here's something from an encyclopedia. They say that in the pragmatic theory, beliefs that lead to the best payoff, that are the best justification of our actions, that promote success, are the things that are true, are truths, according to the pragmatists. All right? So, yeah, it's true if it's useful to believe. And so maybe back in COVID times, this was a pragmatic truth to some of us. I will definitely get COVID if I go to the party this weekend. Right? That's a maybe true, maybe not true. You haven't gone yet, right? But it's a good pragmatic truth because maybe you don't want to get sick. All right? Does that make sense? It's a little weird, but that is somebody's definition of truth. They're all competing with one another. Any questions about that? So that's just extra confusing, right? I'm confused just talking about it, but I'm just trying to tell you, like everything else in this class, all the philosophy stuff that we learn, there is no right answer. There's nothing that you need to spit back to me. You just have to learn to reason. You have to use these ideas yourself. Okay, that's why I'm teaching them to you. So with that, let's go to things that make sense now. Let's talk about stuff that I understand very, very well. It's logic applied to computer science. All right, so let me talk to you about Boolean algebra. It's named after that dude that I talked about on the first day. George Boole was his name. And I'm going to talk about truth tables as well. All right, so in logic, I claim that logic is a branch of mathematics. You can look it up on Wikipedia. It's weird. It's very cool, though. And in logic, we try to use symbols to say what we want because English sucks. All right, English is very hard to say. It's very hard for me to tell you something and for you to fully understand all the implications of what I'm trying to get across. Right? Everything that you can say can be interpreted differently by different people. Right? So English is full of ambiguities, full of contradictions. That's not good. All right. So let's try to fix that by making mathematical symbols that everybody agrees on, essentially. All right. So I'm going to answer this question in this little subsection right now. How can I formally specify the things I'm trying to say so everybody can understand and we can all agree on what it means? Okay. That's a very nice thing to have. I think you can agree. All right. So let's get it. So to motivate the topic, why English sucks when we're trying to talk logically, here is a question for you. All right, I'd like you to go, please, after you've done attendance, go to the written ICE page, and I'll clear it out. I'll have you get into groups, and you can elect a leader, say hi, and all that fun stuff. But after you've introduced yourself or said hi for a minute, here's my question for you guys to discuss and write down your answer to. So this will motivate the idea that we need symbols. So let's say I give you two scenarios. Here's the first scenario. The waiter comes up to your table, and he says, cream or sugar? Right, as you're being served coffee. And then here's a second scenario. Mom says, you can have a cookie or ice cream for dessert. Okay? Both of these sentences use the word or, but they do not mean the same thing, do they? All right, I want you to think about that. Discuss the difference between those two ors in these two scenarios. All right, and try to write down as many differences as you can find. All right, does the question make sense? So please get together with each other, say hi, and then elect a leader to write down this answer, as many as you can find on the written ICE page. couple more minutes. I hear some good discussions. Give me another minute or so. I hear that there's still some typing going on, so I'll let you do that, and then we'll discuss. I hope you came up with some good ideas. Let's see in a few more seconds. Have you considered this difference before? Have you noticed it until now? Before now? It's interesting, huh? All right, I think I hear the keyboard stopping. So here, let's take a look. Let's see if we all agree. The waiter option is more affirmative. You have to choose one. Mom question is more like an option. You can decline both of them. That's a good one. I haven't thought of it that way. That's true. Yeah. Waiter it's open-ended. It allows you to choose either or both. That was what I was kind of going after. Yeah. And then mom is kind of laying down the law. She's like, you can have this one or this one. You're not getting both. Sorry. All right. Does that make sense? That's kind of what's happening. Like you get both the second you have to pick one. Good. Awesome. So thank you for that. Do attendance. If you have not, I want to stop that. I'll stop it the next time I come back. But I hope that makes sense, right? So when the waiter is like bringing you the tray, he's got cream and sugar on that tray. Yeah. And so you are able to have both if you would like both. You can have both. That or means both. It's okay. You can have both. Or one or the other. It's still fine. Or none. You can have both. And then when mom is talking to you, she's telling you what you can and can't do. So you cannot have both. You get one. You get an option. Does that make sense? But we use the same word for both of those. That's not good, right? Because then that introduces ambiguities. If you're trying to tell this to somebody, maybe they'll interpret it one way or the other way, depending on their worldviews or whatever. So we have to fix this, all right? We need a logical symbol now. We need two different symbols, one for the first kind of or, one for the second kind of or, so that everybody can understand which one we meant, all right? So that's where this comes into play. I want to teach you some symbols now. So the logicians, those are the people who study logic, they got together and they're like, all right, here are my symbols. Let's make English not ambiguous by turning it into math. So there's two kinds of ors. It's called inclusive or and exclusive or. All right, let's talk about inclusive or first. There's a logical symbol for this, and it looks like a little V. It's like a wedge symbol. So I'm going to use that in a second. But I would like to show you what or means in terms of trues and falses. And I want you to think about these ideas. It's very like a little mathematical and not very clear. Think of A like cream and B like sugar. This is the waiter's or, all right? This is inclusive or, sugar. And then A or B is like cream ored with sugar, if that makes sense, all right? A ored with B, we'll use that symbol. So this little box is called a truth table. It's a very important thing for us when we study logic. It is giving us all the answers for how this or works, how inclusive or does its thing, because you're oring together two things when you say or. It's like option A or option B. You say that, right? And so you do the same thing in logic. You give option A or option B, just like cream or sugar, and then you want to know if it's true or false, all right? You want to know if it's true or false. And I want you to think of true and falseness as, like, over here. I want you to think of it as somebody's lying to you or not. So it's true if it like checks out and it works. It's false if somebody lied to you. That will be very helpful eventually, all right? But like here is an example of a truth table for this statement. I had cream or sugar. It's the same kind of or as the waiter was telling me. Sugar, all right? Somebody told you this. It was a true statement in any of these cases, all right? So here, let's consider, these are all the options for cream. These are all the options for sugar. It's either true or false. Like I had cream or I had sugar. Either I did or I didn't, right? And these are all the combinations now of having cream or sugar. Does that make sense? Like you had cream and sugar, you had cream but you didn't have sugar, you didn't have cream but you did have sugar, you didn't have either. Does that make sense, those options? With those in mind. But just variables. So the or now, the or is true, like this sentence is true, cream or sugar is true in these three cases, all right? A or B is true. When both of them are true, it's true. Because like, yeah, if you had cream or sugar, like it's true to say that you had both, that's fine. I had cream or sugar, that's a true statement, even when you had both. Okay. And it's still true if you had just one, right? So if you had cream but not sugar, this is still a true statement. You're not lying to somebody. Does that make sense? That's kind of what that means. And then it's still a true statement if you didn't have cream but you did have sugar. It's still the or is true. It's still true to say I had cream or sugar. Does that make sense? That's the waiter's or. The one time you're lying is if you had neither, right? If you said I had cream or sugar, but you didn't, you had. Well, that was fun. They said the word or in that statement. It wasn't an inclusive or. Okay. All right. So yeah, where was I? You're lying in the last case. So if you had neither cream nor sugar, then you are totally fibbing when you say I had cream or sugar. That's the one case when the or is false. Does that make sense? That's the inclusive or. That's the waiter's or. Okay. So that is in stark contrast or to the opposite, the mom's or. That's called exclusive or. All right. But before we leave this slide, I want to show you like eventually you want to like prove or disprove an or, a statement with an or in it. So if you want to prove. Sorry about that. We'll just wait. Weird. So it was a false statement the first time they said this concludes the test. All right. Logic in everyday life. All right. Where was I again? I was on this part, right? I was trying to say like, okay, if somebody like is trying to claim, they're trying to argue that something or something else is true, and they're using inclusive or as the symbol. If you want to prove that an or on two things is true, A or B is true, then you have to just show that you're in one of these three cases, right? Which boils down to showing that at least one of those sides was true somehow, because those are the cases that get you to true on the right. Does that kind of make sense? To prove that the or is true, you just got to show that you're not here. You got to be in one of these other cases, and so at least one of the A or the B is true. Maybe both. Okay, so there's that. And that is the waiter's or. And that's how you prove it. That is in contrast to. Sorry. We need to take bets right now if that's going to happen again. That's pretty funny. Sorry about this, and sorry for those of you who are going to watch this video later. Just like be with headphones on or something. That's going to suck. Sorry. All right, so this is mom's or. It's called exclusive or, it's the other kind. It's the kind where you have an option. It's not one or the other, or sorry, it is one or the other, it's not both. And so the symbol for exclusive OR, sometimes shortened to XOR, is this little plus with a little circle around it. So you'll see that. So instead of A XOR B, some people say this symbol, A XOR B. Still read it like that. And so this is, you can think of it as the cookie or the ice cream example. So you can have a cookie or ice cream with exclusive OR. Cookie, ice cream. And then this would be like cookie, exclusive ORed with ice cream. Usually, this one's more uncommon, and so people usually just use the word OR to imply inclusive OR. Exclusive OR, you always say it. It's like, this is cookie exclusive ORed with ice cream, just to make sure it's not ambiguous. Go for it. So yeah, here's the truth table for exclusive OR. Notice how it changed. I'm going to switch really quickly between the two truth tables. Notice the one place where it's different. Do you see it? It's that first row. That first row is different. Still, the options are the same on the first two, but in the last column, what changed is that you cannot have both. You see that? If they're both true, it was a false statement. All right. So mom was telling you have cookie or ice cream. With the exclusive OR, it was a false statement. She was lying to you if you could really have both. You were only allowed to have one or the other. Does that make sense? So it's false here. Can't have both. You can have one. You can have the cookie but not the ice cream. Then it's true. The exclusive OR is true. Or you can have the cookie but not the ice cream. Or sorry, you can have the ice cream but not the cookie, and then it's also true. Those are the two ways that it could be true. Okay. Does that make sense? And so, like I was saying with false, you want to think about false as if somebody's lying to you. That's what it means for the statement to not be true, right? They were lying to you, usually. So think about false as if someone was lying. All right, so mom telling you you could have a cookie or ice cream with exclusive OR. She's lying in the case where you couldn't have either. All right. And also, if mom told you to have a cookie or ice cream with exclusive OR, cookie or ice cream, then she was also lying if you could really have both. All right, if she was lenient that day. Does that make sense? The only time that she was telling the truth when she said you have a cookie or ice cream was when you had one or the other. All right. And you can also think back to it in terms of this, like I had statement, like I had a cookie or ice cream with exclusive OR is only true if you had one but not the other. Okay, that's how you think of it. So this is the one case that changed compared to inclusive OR. Interesting. Does that make enough sense? Any questions about that? So that's the waiter's OR. And again, if somebody says, like, I claim that A exclusive OR with B is true, to prove that, they have to show you that you're in one of these true cases, right? And they have to show you that you have this guy or this guy, like you got one of the sides, but not both, because that side would be false, right? If you did have both after all. Okay? So, yeah, I think that's exclusive OR. Those are the two kinds of OR in logic. Now let's get to this one, because this one actually makes the most sense. So there's also an AND. OR implies the existence of AND. The symbol is like do a 180 with the OR symbol, inclusive OR symbol. So it's like a, what is that? Another flip down wedge kind of thing. So yeah, upside down V. The and in English is actually not ambiguous. So that's really nice. The and is just the and from English. So this is perfect. Let's see here. So again, the symbol looks like this, A ANDed with B. And then here's the truth table for AND. It's only ever true in this first case where you had both. You had A and B. Does that kind of make sense? So here's a sentence example of using AND. Maybe the waiter comes and tells you instead, we have cream and sugar. If I can spell right. Something like that. So that's the and, right? We can turn that into a logical statement where the first side is cream, the side is sugar, and then like the waiter's telling you cream and sugar is true, yeah? And so for him to not be lying to you, it must have been the case that there was cream and sugar in the back for you to have, yes? It's the only way that would work out. The waiter was lying to you by saying this, right? If the user said this, or not the user, but if the waiter said this, He was lying if there was really just cream but no sugar, right? It was false. It was wrong. It was a lie to say that there was cream and sugar. Yeah. Same with if there was sugar but no cream, it was still a lie to tell you that there was cream and sugar. We have cream and sugar. Right? So the and is only true if they're both true. And then he was definitely lying if there was no cream and also no sugar at all. He had nothing. It's totally lying to say there was cream and sugar, so it's false there too. Right? So the one time he was telling the truth is in this case where there really was cream and sugar for you to have both kinds. Okay. Questions about that one? That one's, I would say, a little bit better than the ors because like the and does translate pretty easily to logic. Does that make enough sense? And so again, if somebody's trying to prove to you in logic, I'm proving that A ANDed with B is true. Again, they got to show that they're in one of these cases, not just this case, right? They got to prove to you that both A is true by itself and B is true by itself, because that's the only way that their and can be true. Okay? I've said some weird words. Are we following them? You're learning it? All right. So you got to prove that you have both at your fingertips, both pieces. Okay? There's one more main one now that I want to talk about, and this one's very simple because it only takes one thing rather than two things. So this one's called the not, or the logical negation. It just flips the thing. The symbol looks like this, and I like to think of this as like a diving board. It's like a person on a diving board. This can be your metaphor, and like they're about to do a flip before they go into the pool. Because what the not does is it flips true to false and false to true. Right? So yeah, the negation of a statement, not A, just like if it was true, the negation makes it false. It turns it into false, and it turns false into true. Okay, that's what it does. It just flips the thing. And so here's an example statement that we could think of using the negation, using not, logical not. Let's say that the waiter says, "We don't have cream." All right. So essentially then, what the waiter is telling you is not cream is true. Does that make sense? That's what's going on there. And so like if this were cream, the negation, which they're trying to claim is a true thing, works like this, right? So the waiter was telling you the truth by saying we don't have cream, not cream is true, in the case where there really was no cream. Does that make sense? It's flipping it. It's flipping it like that. The waiter was lying to you if they just didn't want to give you cream. They were lying to you if there was cream in the back and they said we don't have cream. Okay? You see how that's working out? It just flips the thing. Okay? Any questions about that one? So yeah, we got a bunch under our, in our little tool belt now. We have all these options, inclusive or, exclusive or, and my PowerPoint just crashed? Or no, that was just the screen, sorry. Okay, we're back. And then and not. All right, so we got all these things. And okay, one last one. If the user's trying to prove to you that the negation of something is true, right? Again, they have to show that they're in this case and that the original thing was false. Right, the thing being negated. You got to show that A is false, and that's that. So a very cool thing is the following. Let's say you have a bunch of variables. You got a bunch of like variables in your statement that you're trying to make, like cream, sugar, cookie, ice cream, all these things. And you make some big long statement with a ton of like just ands, ors, and nots. Like whatever you want to represent. Let's like you have some pie in the sky idea. Let's not even say you're using and, or, or not yet. Like you have something, and like you have a bunch of options for your variables, and you wanted to make sure like your something is only true here, false here, false here. Like you're trying to make a truth table essentially. Let's say that what you really want is true when it's right here, false when it's right here. Like all these things in that exact order. Maybe false here, true here, all the way down for every different option. Like whatever you want, whatever your dream is for your truth table, whatever you want to create there, I claim that you can create it using nothing but and, inclusive or, and not. Just this guy, and this guy can build you any combination of trues and falses over here in any order based on your variables. That's very powerful. That's very, very cool. You can express any truth table you want with some combination of and, inclusive or, and not. All right? That's pretty fun. So let me show that to you. All right? Exclusive or was not one of those. So exclusive or can be created using and or and not somehow, or some combination of them. Let me show that to you, all right? Let me prove that. I'll construct it for you, all right? I'll give you the answer, but I'm going to give you a truth table, and I want you to try filling in the truth table like with your hands, because that's really, really useful, okay? So here, the secret is A exclusive ORed with B. A exclusive ORed with B is logically equivalent to the following. It's logically equivalent to not A or B, and, or sorry, excuse me, not A and B. Not A and B, either A is true and B is false, or A is false and B is true, or A and not B. A is true and B is false. All right? That is the big long thing that is equivalent, I claim, to exclusive OR, and we're going to prove that together. All right? So let's figure out the truth table for this big thing. All right? And it seems very weird, but it's just made up of two variables, so let's put two variables over here on the left. So I'll get you started, and then I want you to fill this in, okay? I'll show you the symbols in just a second. I'll give you back the truth table. But there's all that. And we know that, like, here's the trick. A and B, they're two different things, can be true or false. We want every combination of them. For two things, it's always like this. It's always true, 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 false. It's a standard order. False, true, false, false. Those are the variables values. And then to build this giant thing, well, you can see like it's going to use pieces, smaller pieces. It's going to need not A and not B. So let's go build the truth tables for those. Not A, what's not A, and for these cases for A, what's not B. And then we'll have them to use in the bigger things. Then we can and together the not A and the B because we have both on the left. Does that kind of make sense? So we'll take that and we'll then create not A anded with B because we'll have both sides at that point. And I'll do the same with this one. I can do A and with not B because I'll have the A here and the not B I'll already have filled it in. A and not B. And then finally, I got these two things. I will be able to OR them together finally to get the final answer. All right? Not A anded with B, ORed with A anded with not B. Okay? And then I will prove to you that that is all equivalent to A exclusive ORed with B. All right? Let me show that to you. I'll do it in rainbow. A exclusive ORed with B. We can fill this one in first. A exclusive ORed with B is true if just one side is true, right? So it's the middle ones. True, true. And it's false on both sides, right? Can't have both. Can't have neither. That's the exclusive OR's truth table. And then let me do some other ones of these, and then I'll like try to make a screenshot on here for you so like you can see them all while you're trying this. But let me fill in like this one. All right, for you, and I want you to fill in the rest. So, all right, starting with these values, these are all the options for A and B. Like, what is not A in all these cases? Well, it just depends on the A. So, like, if A is true here, not A is false. It got flipped. Does that make sense? That's how I'm following that. If A is true again, then not A is flipped to false. If A is false, it gets flipped to true. So that's how you fill in these columns. False becomes true again. You do the same for not B, then you'll do the and on them, then the or on the things that you've had already. So it's just building up the answer slowly but surely. Does that make sense, the process? So here, let me give you all of the ones you'll need. Here is or. This is inclusive or. I'll give you this one, so you can have it on the page. I want to give you some time. You don't have to do it on the written nice page. I really want you to write it out and help the people sit next to you. All right, this is how you learn it. And then there's and. Truth table, and then I'll give you the not as well. Those are all the ones we're using. All right, that's as big as I can make them. But I'd like you to fill in the rest of this. Get trues and falses, 4 on each row, right? For these different combinations of A and B. But eventually, you should find check your answer should be equivalent to the other one. Okay. Questions about the question? Yeah, please give this a try. I'll give you a few minutes to get a try in there and fill it in, and I will come around and help you if you're struggling with anything. Please raise your hand and ask questions. Yeah, help each other. Try to complete the truth table. It's very good practice. Oh, and sorry, it looks like the symbol didn't come with it. So this is or, this is and, that is not. Okay. All right, I think that was enough of a head start. Let me go through the rest of it. All right, we got. I'm gonna erase these. Well, not B. Just flip it, right? It's just flipping this entire thing. So true, false, true, false becomes false, true, false, true. Oops. Yeah. And then, let's see what else. Then we've got both of those things. Now we have the not A, we have the B. We can AND them together. And honestly, the order doesn't matter. You can do it on either side. But I'll do it with not A on the left. So, all right. If not A is false here and that with B, the answer is going to be false, right? Anything. If there's a false anywhere, the AND is always false, right? It's only true if they're both true. So, all right, there was a false somewhere for that one. So the AND is false. And then, all right, not A here is false. I don't even need to look at B now because I know the answer is false. It's never going to work. So that kind of makes sense. That's the trick that you can think about. Not A here is true. Okay, could be true. If B was true and B is true, nice. So that one's true. This part's true. The AND is true. And then not A, AND with B, true AND with false. Darn. B was not helping our case here. All right, so there's that one. Does that make sense? That's how I fill in that one. And then the same one that's kind of symmetric. We got A AND with not B. Let me just make sure I didn't mess that first one up. Yeah, A AND with not B. You can immediately see that you have some options here. So A is true in both of those cases. So it's really not B is telling us, like, is it true or false? Because it's only true if they're both true, and A is true. So it's just going to essentially be whatever not B is here. So true AND with false, sadly false. True AND with true, though, is true. So it's false, true. Cool. And then for the last ones, you can see that A is false. So I don't even need to look at not B. I know the answer is going to be false. For the AND. Cool. And so it's like this one is picking out the case where A is false and B is true. You can kind of read it out of the thing once you get used to it. And then this is picking out the case where A is true and B is false. Can I see that? False everywhere else. That's neat. And then when you OR them together, it's true if it's ever true anywhere. So, like, it's just these guys ORed together. It's true if there's true anywhere. This one's false both times, so one time it's still false. This one, false OR with true. Well, one side's true. That first one's supposed to be false. Then true. True OR with false, true. One side's true, or both. False OR with false is false. And do you see, after all that work, it's equivalent. It always lines up. So this is the same, logically equivalent to exclusive OR. You didn't need the symbol exclusive OR technically. Any questions about that? That's very cool. All right. Yeah, are we good? We good to keep going? Because I have more difficult examples after this. I'll have you try. So truth tables, very useful. We've just shown that and, or, and not can build anything. There's more to that actually. Here's 2 new truth tables that I'm not going to force you to memorize or anything. The other ones you need to know. These ones are just cool, and I want to show you why. So this is called NAND. This is an operation called NAND. It's over here. It's really just a combination. Everything is a combination of and not. But like you can make just in one fell swoop a thing called NAND, and what it really does is it does the negation after anding together 2 things. All right. So first you do the and. Then you flip everything true to false, false to true. That's called A NANDed with B. And then likewise, there's one called NOR. So A NORed with B is the same as first taking A ORed with B and then negating it all, flipping it all. Okay, so there's NAND and NOR, and they are both what's called functionally complete, which is very interesting to think about. So first of all, and, or, and not, those are functionally complete. Another phrase for the idea of you can make any truth table with these things, it's called functional completeness. All right, so and, or, and not are functionally complete. And truth tables, like there's a very complicated truth table that becomes a microprocessor. This is why we're learning this. I want to tell you that right now. You can build a truth table for how a processor should work. You can build a computer using and, or, and not. All right, that is why we're learning it. It's that important. So cool that is possible. The only thing extra that you need is like a little signal that goes high and low called a clock. That plus and, or, and not gives you a computer. All right, it's very cool to think about. I can't explain fully why, but that's a thing. And so and, or, and not, very important. So they can build you a processor, more or less. And then NAND and NOR are even cooler because by themselves they're functionally complete. So just NAND and just NOR. So just NAND by itself is functionally complete. Apparently, you can build and, or, not out of just NAND if you had that as your basic operation. NAND is functionally complete. Same with just NOR. So and, or, not, they make more sense. But in a computer, it's cheap to just make the same thing a bunch of times. So like everybody who's building a processor, they just go to NAND to Costco and they buy a bunch of NANDs and they just build the entire computer out of NANDs operations because they can build and, or, not out of that. All right. Same with NOR. You can do the same thing with NOR. You can go to microprocessor Costco, get a bunch of NORs and hook them together, make a computer out of it. So it's cheap to buy in bulk, I guess. But that's an interesting idea, right? Functional completeness. You can build any truth table with and, or, not, or these guys. All right. So let's break down some like English sentences, because that was one of the things I was telling you that logic is good for. You can break down English sentences and keep it from getting ambiguous. All right. So here's something that we might care about if we were a child. Let's say that Dad tells us, "I will give you $20 if you clean the bathroom and." Notice the parentheses, and mow the lawn or do the dishes. All right. See how I'm saying that? Can we parse that? Does that make sense? So that's what Dad is telling us. And we, as scheming young children, we really would like to get $20 with the least amount of work. Right? This is where logic can happen. This is where logic can come into play. Because like, what is this? But Dad's saying something is true if clean the bathroom A, mow the lawn B, and then do the dishes C. Dad is telling us we get $20 if the following is true, right? A anded with B or C. Yes? And so now we can build a truth table for that and figure out what is the minimum amount of effort that will give us $20. Yes? That is our goal right now. All right? Under what conditions are we guaranteed to get $20? Logic can apply here. It's very useful. You build a contract with Dad using logical symbols if you want to. Okay? So let's make a truth table for this exact formula. So here it is again. Again, this was A, this is B, this is C. And so the full thing is A anded with B or C. That's useful. And then let's build that truth table. All right. It's got 3 variables this time, so it's going to be a bit longer. Because you got to try every option. You got to write down every different possibility for trues and falses for each of these. There's going to be 8 options because each of them, A, B, and C, can have 2 options. You kind of multiply the options together. So it's 2 times 2 times 2 options total. Okay. So the standard order is this. This one alternates true, false, true, false, true, false, true, false. This one alternates twice as slow. So it says true, true, false, false, true, true, false, false. This is an easy way to get all the options quickly. And then this one alternates twice as slow, even more, even another 2 times twice as slow. So it's true 4 times, true, 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 false, 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 false. And if you think about it, these are all the 8 options for trues and falses for A, B, and C. Every single possibility is there. If you want to get technical, what's really happening, the standard order is you're counting down in binary, which I have not yet taught you. Okay, you can come back to that in a second though. But okay, I want to build this formula. So an intermediate step would be B ORed with C. So let's make a row for that. B ORed with C. And then we can use that, and we can add it with A to get our final thing. A ANDed with B ORed with C. Yeah, that's the goal. Yes, let's do B ORed with C. So it's true, and OR is true if they're both true. Sorry, it's true if either one are true, including both. So true ORed with true, inclusive OR is true. B or C. B is true here again, true ORed with false, true. False ORed with true, true. False ORed with false, sorry, false, darn. And then I'll just do the other ones quickly. So true ORed with true, true, true ORed with false, one's true, false or true, false. Okay? Does that make sense? That row that I just got? Do yell at me if you have any questions about this. This is important to know. And then finally, once I have this one, I got that over here, and now I want to AND it with A. So the AND is true if they're both true, only if they're both true. So A is only true for these 4, so I know for sure there's falses down here. Just immediately. Does that make sense? I don't even have to look for the last 4 rows. It's going to be false, 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 because A is going to ruin our party. Okay, because it has to be true on both sides for the thing to be true. So the first 4, though, possible. Excuse me. So let's see, how does it stack up for these first 4? It looks like it's true both times for the first 3 rows, but B or C is false on the last one, on that 4th one. So that's where it will be false one more time. And these are true. So true, true, and it was true. That's the only time you get true. Does that make sense? And so our goal, right, was to say, if Dad is not lying to us right now, what are the cases where we could get our $20? We have just found that there are 3 cases. You see that? There are 3 ways to get $20, and let me talk to you about them. So apparently, we'll get $20 if we do all 3 things. If we clean the bathroom and mow the lawn and do the dishes. Yes, that checks out, right? We're just extra good children. That would work. We'd get our $20, but we're lazy. We probably care about one of the other cases. So, all right, this one is saying that it's true if we did it this way. If we clean the bathroom and mow the lawn, but we didn't do the dishes. We have that option with the OR, right? We'll still get $20. Okay, maybe we want to do that one. And then finally, we'll get $20. It's true if we clean the bathroom, don't mow the lawn, but we do the dishes. Okay. Those are the 3 ways that we will get $20 if Dad is not lying to us. Yes? Are there any questions about that? That's kind of useful to know how to do and be able to do. There's no ambiguity. We can just take an English and turn it into a truth table, and that's important to do. Powerful stuff. You can build a computer out of this. So, if we are happy, I have a hard one for you to try now. Okay? Dun, dun, dun. I would like you to create a truth table for this formula. A ANDed with B first, ORed with B ANDed with not C, the negation of C. Okay? I'd like you to try that one. I'll give you the start. Let me write it down, and I'll give you a head start as well. I'll eventually do it too. But here you got 3 variables, and so just like I was doing before, let's write down all their possibilities. Drawing straight lines decent today. Gonna knock on wood. All right, so those are A, B, and C. So the options for A, B, and C are, this one likes to alternate. That's a false right there, and I just made it worse. And that's a true. But yeah, do you see what the intermediate steps might be? You just erase me because I'm trying to write pretty. You don't have to write pretty. True, true, false, false. True, true, false, false. And then this one goes even more slowly. 4 trues and 4 falses. Those are all our options for A, B, and C. And then I would say the intermediate steps would be, all right, I can do the A ANDed with B immediately. I got both of those. A ANDed with B. And then I need to do not C in order to do this AND, right? So let's get that ready. Not C, I'll need a row for that. And then once I have the not C row, I can take the B and AND it with it. That'll work. And I can do this one, B ANDed with not C. You don't really need the parentheses there. I'll just write it like that. And then finally, once I got that, I can take both of these, right? Because those are both of those sides, and I can OR them together. So that will give me the final thing. So I can have my A ANDed with B, ORed with B ANDed with not C. Okay, I think that's right. So that's like the logical progression of things. And you can remember that the not means flip it. So here, let me just give you the and the OR. And I think I'm going to give you this inclusive OR. Usually, it's inclusive OR when we say OR. There you go. So yeah, try it, help each other, help your neighbors. Let me know if you have any questions, but I'll give you like a minute or so. Try to fill it out, and then I'll show you my way, how I think about it. I'll go faster because I've been doing this. And usually our goal is like, which ways are there that we can make true in the final way too hard. Just on paper is where you can practice. Take a minute to try that. Alright, that's my timer. I'm gonna go fast and try it now. But keep working if you'd like. Alright, and with B, what are my options? True and true. True. I'm just gonna go through it now. True and true again. False. True and false. True and false. It looks like it's false everywhere now. Is that correct? Yeah. Like A is now false. So it's got to be false. Then not C is just flipping, right? Flipping what C is. If C is true, it becomes false. C is false, it becomes true. False, true. I'm just going to alternate because that's what it's doing. False, true, false, true. I'll try to line it up. False, true, false, true. And then now I got both things. I got the B, I got the not C. I can AND them. It's true if they're both true. True and with false. False. Nope. Not going to work. Not C ruins the day. True and with true. Ooh, that one's true. Cool. False. It's hopeless. False. False. Still hopeless. False. Ooh, true. Maybe. And nope. But we got a false over there. False. And then true. True. Ooh, nice. Cool. There's a true there. And then we've got false for B both time, so it doesn't even matter what not C is. So it's going to be false. Okay, so those are those. And yeah, I think that's it. Let me OR them together now. This guy and this guy. OR together make true, true. And then it's got two falses, make a false, 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 or with false, false. Ooh, a true. And then two falses. All right, so at the end of the day, it looks like there's 3 ways to make true for this statement. This one, this one, this one. And they come from these options of A, B, and C. That one, and that one. Any questions about that? Does that kind of make sense? We're getting the hang of it now. Practice. All right, so yeah, like I was saying, the reason we're learning this is because I want to teach you how to build a computer, essentially. You'll have to wait until CSCI 45 to fully understand this stuff, but I can answer this question. I guess I already kind of have. Like, all right, this is nice. I like pushing symbols, but like, how does this give me computers? You can turn all of these operations, and, or, and not, into operations on electricity. You send in power, the negation would send out no power, essentially. That's how it would work. There are circuits that you can build now, and they're called logic gates. These are physical devices that you can build that take voltage and spit out the correct answer in terms of the logical truth table for that operation. All right. So inside of a computer, true and false. They're not like written or anything. They're not true and false. They are true is like a 1 and false is like a 0. That's one thing you can think of. And then really deep down in the circuits, like a 1 is high voltage, true is high voltage. And then a 0 is low voltage. Okay, so become a computer engineer if you want to learn more. But here are the logic gates and the symbols for them. So this is called the AND gate, and you can kind of read it from left to right. So these are the inputs to the AND gate, and it does the AND somewhere here inside of it. It's just the symbol for it. And then it spits out the AND of those two things. That's how it works. It takes the input, feeds it that way, and gives you the ANDed output. And then this is the OR gate. It's kind of like a curvier version of the AND gate. And I like to remember it like it looks like the bullet from Super Mario. And the OR is like the curvy version of that. It takes an A and B, and then it spits out the OR of the two. And then the NOT gate looks like this. I want you to think of the NOT happening at the little dot, because that's useful for other things. And it just takes in the thing, outputs the negation of it. And then another word for the NOT gate, like this is the AND gate, the OR gate, the NOT gate. Another word for NOT gate is inverter, because it inverts the signal. Inverter. And then these are the ones I care about you knowing. All right, those are the AND, inclusive OR, and NOT gates that you can build computers out of. It's very cool. This is what NAND looks like, and that's why I told you to think of the dot as negation, because NAND was do the AND and then negate, and the NOR was do the OR then negate. And then exclusive OR looks like this. It's like take the OR but add another slash here. So this is the exclusive OR gate, XOR gate. Okay, and so once you come up with a logical formula, some formula for the computer you want to do, like you want to take in your inputs and produce some true or false output. You want to produce a truth table. Given your truth table, you turn it into like the final formula, and then you take the formula and you put it with these circuits. You build it out of them. Okay, so like here's an example of building a circuit out of our gates. I'll just use these guys, but here they are. These are the options that we could use here. Let's look at it. So this is how you would draw the schematic that you'd give to an engineer or something. You're like, all right, I've got 4 input variables, A, B, C, and D. And those can be wires coming in now. Does that kind of make sense? Those are my inputs, like high voltage or low voltage, who knows? Like whatever, connected to a light switch or something. And then, all right, I want to build this final thing, not A and B, ORed with C and not D. So I kind of need those two sides first. I need this side and this side, and I can build them slowly but surely. To make this side, I need not A first, so let's take the A wire and send it through the NOT gate. Does that kind of make sense? Because now coming out of this now is not A. And I can take it with B and AND it with an AND gate. I can take it right here and put it into an AND gate, the A, or the not A, and then the B. There they are. And so now coming out of this is not A ANDed with B. Does that make sense? That's what's gonna happen. You can build this circuit when you put the wires in this way. And let's do the other side now. C AND with not D, so I need to take D and invert it. Get not D coming out of here, not D. And then I can AND it with C. So take the C wire, feed it through an AND gate with the not D. Just like that. So coming out of this is, as you can expect, C and not D. And then finally, I got both of those pieces. I want to OR them together. I got one piece now, one piece on two different wires. I want to OR them together with an OR gate, and that looks like this. Okay? So take them, feed them to the OR gate. Boop. It's always hard for me to draw the OR gate. Looks like that, curvy. What we do, like that's one side, that's the other side. Feed them in, and then come out of here is your final answer. There's your not A, AND with B, and we just ORed it using the OR gate with C and with not D. Okay? And so, yeah, you feed in input, feed in voltages, it would spit out the right answer, depending on your inputs for that truth table. Are there any questions about that? So there are pieces, like you can buy these pieces in an electronics store or something, and you can build this circuit. And it's kind of cool. Oops, spilling water on my computer. I'll fix that later. Good enough. So yeah, with that in mind, you try. This is where we're going. You can build a computer out of these ideas. So your turn. I would like you to build a circuit for this expression. All right. B ORed with not C, and all that ANDed with not A ANDed with D. All right. So here is, I can give you my circuit too. Like here's the first bits of it. Something like that. So like there's my starting point. You can feed it in. Does it kind of make sense? So you'll do something similar to that. I want you to try that. All right? Try to make what I just did. This is the old answer, but with the new one. All right? Maybe you'll have to rearrange the order of things. That might make it easier on you. But use the gates, add the wires, and compute this final answer. Try that. I'll give you a minute or two. And so for all except the not gates, we got two inputs coming in. Supposed to only have one. Let me show you how I might approach it. Any questions though as we tried it? That won't be answered by me just doing it. All right. So here, let's put these up here or something for a second. Yeah, so I don't know. Let's be lazy and just do them in order. A, B, C, D. Probably a bad idea. We'll figure it out. And then, all right, let's do this side first. B ORed with not C, so I better negate C. Send it in to a not gate, and there's not C coming out of there. And then take B, OR it together, so I'll use an OR gate. So, looks like that, right? I can draw that better. Give me a second. There we go. So take the B, take the not C, feed them in. Coming out of here is now B ORed with, not C. Cool. And then we've got what else? We need not A and with D now. So, okay. Like this is coming this way. This wire is for sure going that way. Now I need not A, so I can negate A. There it is. And I need to give that to, with D, into like an AND gate here. Let's put the AND gate down here. Interesting. So I guess it's useful to do it in this way because here's how you jump over a wire in your drawing. Boop. You do it like this. You say whoop. That's the symbol of you jumping over the wire. Oh shoot! Why is PowerPoint trying to be weird? There it goes. That's you jumping over the wire now. All right. That's how you like show that they're not connected right now. Because otherwise it would like short the circuit or something. Who knows? And then you can end them together with the two things you wanted. So that now is not A ANDed with D, not B, sorry, with D. And then the final answer is take those two sides and AND them together one last time. So here's the AND gate. One last time. Boop. So that's that one, and there's my answer. Okay, so I think that's most of what I wanted to say for the last 5 minutes. I just want to quickly talk about a new idea. It's a number system. It's called binary. I'm sure you've heard of it by now. It's what computers think in. But at the end of the day, it's just a way to write numbers. And so I want to just kind of get started with that, and then we'll talk about it more later. So it's like it's ones and zeros, but that's probably as much as you know right now. Like, how does that apply? So first of all, like I said, 1 is true or high voltage, and 0 is false or low voltage. And all of our computers, all they are is just a bunch of logic gates jumbled together and then a clock signal that goes high and low. It's crazy. That's all you need to build a computer. And then everything you put inside of a computer as well, in addition to like the electricity that's driving the processor, all the stuff that you store is in binary as well. So like everything, all of your files, this PowerPoint is made up of ones and zeros as well. Okay. And that's binary. Binary is a number system, and it looks like this. All right. So we as humans use what's called base 10. That's decimal. Another name for that. Those are the numbers that we use in math. Binary is base 2. All right. In base 10, by the way, the reason we call it base 10 is because you have 10 digits to build your numbers with. So here are all the 10 digits, right? There's 9, up to 9. That's 10 total. 10 digits total to build our numbers in computers, or in math. And then once you want to add one more to the last digit, like 9 plus 1, that equals 10. Right? That's why you need a new base, or sorry, a new place, excuse me. And so there are other number systems. There's one called binary. Binary is base 2, and that means you only get 2 digits to work with. To build up your numbers, you can only have 0 or 1. Crazy. And so 1, 0 could technically be a binary number. It's got ones and zeros in it. So I have to be very careful. I have to tell you what numbers are written in what base. So if this means 10, the 10 that we know, I'm going to use a subscript to say this is the decimal number 10. Like this is 1, 2, 3 in decimal. I'll use that subscript. Rather than like 1, 0 in binary, right? So binary works like this. Like it goes 0, then 1. Those are your 2 digits. And then if you want to try to add 1 and 1 in binary, the answer is, well, you run out of digits, so you have to add a new place. It's 1, 0 base 2. Isn't that weird? It's not the same as 10. You add 1 to that, it's 1, 1 base 2. That's 3 in binary. Add another 1 to that, it's 1, 0, 0. Got to add a new place already. 1, 0, 0 in binary. That's the number 4 in binary. It's crazy, right? And so a bit is short for binary digit. So this is a 3-bit number, right? And then this is like 1, 0, 1, 1, 0, 0. That's a 6-bit number. I got 2 minutes left. And then finally a byte. A byte is just a unit of space. It's an 8-bit binary number, right? You got 8 binary digits. And so, for example, this is a byte. 1, 0, 1, 0, 1, 0, 1, 1. Just like any string of 8 binary digits make up 1 byte. And that's like a number. And you can figure out what it is. And do pay attention to the base when I use it, because like 1, 0, base 2, that's binary, right? That's the number 2. That is absolutely not the same as 1, 0, base 10, decimal. That's the number 10. 2 versus 10. Any questions about that? That's where we're going, and I'll teach you how to think in binary next non-programming lecture. I think that's all I got. That's where I'll stop. And bit is short for binary digit. They took the B and the IT. That's what I was trying to say. What else was I going to say? Oh yeah, and we, as humans, we think we use base 10 because we have 10 fingers. So maybe in the Simpsons world, they'd use base 8. Who knows?
I just want to let you know I'm not going to be here next Monday.
Okay, that's fine if it's like something that's excusable, like send me an email. So I
My
can,
wisdom teeth out.
that's definitely excusable. So yeah, please send me a Discord message or something. I'll make sure that doesn't count towards the 3 consecutive whatever. And good luck. All right, I'm going office hours right now. If anybody has any questions, you can follow me there. Yeah, what's up?
You're gonna get tested on this, right?
Yes.
So that first example that you said, you brought in, because I know that APMC, right? Remember that first example that you explained?
Yeah, I'm trying to write down just every possibility for the combinations of what A, B, and C could be, all the different trues and false.
So like for like these two, right? Like you start out with like kind of
Yeah,
these two, and then false, and then you flip
false, true, false, false. Yeah,
right? So then like when you brought in that second, that third one,
now there's even more options.
but like uh you listed quite a few possibilities.
Yeah.
But I don't know. I didn't like. I don't know how you got
Okay,
the
yeah.
rest of them.
So the order doesn't matter as long as you have every option, but you can try it. Can you try writing every single possibility?
I don't. No, I don't have one.
Because how I was doing it when he was explaining to it, I would highlight the ones where it said when you started circling it, and then he went over to it, and then it went to true or false. I would highlight when he said
Yeah, I will.
so you could see it better.
Yeah.
That's how I remembered it.
But it's basically the order doesn't matter as long as all
You
the
have every
possibilities
possibility. Okay, we can use your paper if you like, because then you can have it later.
Sorry, a blank page.
Yeah. Here, if you have a three-variable
Yeah,
formula,
three of them.
let's write down what's going to happen. So it's A, B, and C again.
Yeah, it's like it's-
Got other things. A, B, C. Yeah, something involving A, B, and C over here, of course. So all the options are going to be 8 total. Does that make sense why it's 8? Because like you have true and false for A, true and false for B, true and false for C. You want to try every option. It's going to be 2 times 2 times 2. That gives you the number of the possibilities.
So for AB, it's only
Only 4.
4, right? 4.
Yeah. And that's easier to look at because I'm sure you wrote that. You can see that all the options are covered there. And
True,
look at my
false.
But the trick is you start with the rightness one, and like this is a standard order. It doesn't have to be in this order, but it will give you all the options. You start with true, and you just alternate it every time. So it's true, false. You know that there has to be 8. So it's true, false, true, false, true, false. So it's alternate, and then the next one you go one over, and then it alternates twice as slow. So it says true, true a little bit longer. True, true, false, false. True, true, false, false. That kind of makes sense.